Hi everyone, this is Dr. Sandeep, Associate Professor in the Department of Mechanical Engineering from Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the phase diagrams. So what is the importance of a phase diagram? So this phase diagram is very important in identifying the characteristics of any material. Suppose if any given metal is there, if you want to find out what are the characteristics, what are the properties, what is the correlation between the properties as well as the characteristics of the metal can be identified with the help of a phase diagram. So in general, what is the phase means? One phase is transition to other phase. That means from solid state, if a body is being converting into a liquid state, so that is called as a phase transition, phase transformation. Okay, it is a phase. That means a body which in a solid form, it is called as a solid phase. And similarly, if the body is in the liquid state, then that type of body is called liquid phase. In similar cases, in some cases, it can be combined of both solid as well as liquid phases. So for any type of body, we have different phases that also depends upon the temperature. Okay, so if you know the phase diagram of any metal or any material, then it is easy for us to identify what is the melting temperature of the material, what is the properties of the material, what is the characteristics of the material, and even also you can identify the microstructure of the material. So these are all depending upon the phase transformations. That's why one need to understand or one need to study the importance of the phase. Why? Because these are interrelated to its properties. As I told, this phase transformation or phase diagrams help us to identify the properties, the melting temperatures, the characteristics, even the microstructure of the given material. So this is how the phase diagrams are very important to us. Now, why to understand the phase diagrams means this phase diagrams of any type of alloys gives the correlation between the microstructure as well as the mechanical properties. So that's why these phase diagrams are very important for us. What it is giving? It is giving the correlation between the mechanical properties as well as the microstructure. That means, suppose if you take any metal, if you take suppose a copper metal, if you are heating this copper metal from 0 degrees centigrade to 100 degrees centigrade, so what is happening? At every temperature, there is some change in the microstructure, as well as there is a change in the phase. That means slowly it is converting from the solid state to a liquid state. So all these are interrelated to each other. That's why the phase diagrams gives the correlation between the mechanical properties as well as the microstructure. And these microstructure can be visible to the help of a microscope. You can't see the structure of any type of metal with the naked eye. So with the help of a microscope, you can see this microstructure. And the development of microstructure of an alloy to the characteristics of the phase diagram. And also you can develop the microstructure. How you are going to develop the microstructure? If you add the alloys to the metal, that means a substitute to the metal, then what we can do? We can improve the microstructure as well as we can improve the characteristics of the given metal. So that's why if you try to understand the concept of phase diagram, also if you understand how to draw the phase diagram, then it is very easy for us to categorize them. Suppose if any metal is weak in section, weak in mechanical properties, so what can you do? You can improve the characteristics by adding some alloys. Similarly, if the microstructure is in a weak, suppose the nuclides are very less, if you want to improve the nuclides, what you can do? You can add some additional alloys. So how can you do all these things? With the help of the phase diagrams only. That's why the phase diagrams are very important, in which you can correlate the microstructure as well as the mechanical properties of the given metal. In addition to this, what the phase diagrams are going to do? They are providing valuable information about the melting, casting, crystallization and other phenomena. Not only it is giving the mechanical properties and the microstructure, Rather than this, it is trying to give the melting temperature. So one need to know, if you want to do any manufacturing process, what you will do, you have to melt the raw material. At what temperature you will melt? So that can be identified with the help of the phase diagrams. That's why this is giving a valuable information. The phase diagram is giving the valuable information about the melting temperature of any given metal. Suppose in some applications you need to do with the help of cast iron. So how can you identify what is the melting temperature of cast iron? If you know the phase diagrams. Similarly, copper, nickel. So like that you have n number of components. So these components, we have to identify what is the melting temperature. Once we know the melting temperature, then it is very easy for us to do the manufacturing process. That's why it will give the information, the additional information, rather than the characteristics as well as the microstructure. It is giving some valuable information about the melting temperature. Next is the casting temperature. So casting, at what temperature you have to do the casting process. That means at some point of time, you have to do the casting. You have to pour the molten metal into the cavity. So at what temperature? So that temperature can also be identified with the help of the phase diagrams. Similarly, it is giving the crystallization temperature. Crystallization. So once you heat the metal, what happens? Inside you have grains. So all these grains, at some point, they may be irregular or regular. So if any irregularities are there, so what is happening? At that point of irregularity, you'll have a less strength. You have weaker section at the junction. So in order to compensate, in order to have a uniform distribution of the grains inside the body, what you have to do? You have to heat the metal. You have to do some heat treatment process. So that heat treatment process can be identified with this crystallization. So these are all some of the important informations we can get from the phase diagrams. So one is the mechanical properties, another the microstructure. So apart from these, we can get the information about the melting temperature, casting, and the crystallization temperature and other phenomena. So these are the very, very important characteristics to identify the metal characteristics based upon the phase diagrams. Now, the graph, whatever the graph I'm showing now, this is an example of water. So how this water is being converting into three different phases, we will see now. And what are the three different phases are there in this phase diagram, and how to draw the phase diagram of a water. If any question is coming, that to draw a phase diagram for water, so this is the procedure you have to follow. This is an example for water. Similarly, for any other type of metal, to draw the phase diagram, we'll see what are the steps to be followed. Now here, the below graph is a phase diagram for water. So in this case, what we're trying to do, we're taking the x-axis. So this is my x-axis as temperature. Okay, x-axis as temperature, starting from minus 20, 0, 20, 40, 60, 80, 100 and 100. That is about the x-axis. And if you go with the y-axis, this is the y-axis, you have pressure. So it is starting from 0.001, 0.001, 1, 10, 100 and 1000 atmospheric pressures. So these are the pressure values along the y-axis, and along the x-axis you have the temperature. Now how it is being converted into different phases? How we are getting those phases? So generally water has three different phases. What is it? What is the solid phase here? An ice cube is an example of a solid phase. So if you wanted to convert into liquid, so when it is in a liquid form, that is a liquid phase. Now if it is in a vapor, that is the vapor phase. So three different phases we are having for a water. So how to draw these three phases, we'll see. Now we have x-axis the temperature, y-axis as the pressure. Now here, what are the phases, familiar phases we have? Solid ice. Okay, solid ice, then water, then steam, that is in the form of vapor. So these are all the three different phases what we're having. And now what are the red color you're seeing here? These are the boundaries that are defined with the help of the region. Boundary. If you cross that boundary, the phase will change. If you cross another boundary, the another phase will come. So like that, for each phase, you have each boundary. Now if you see here, first boundary, This is the first boundary. Whatever you see, this boundary comes under solid ice, solid phase. So which is in the form of an ice. So it is approximately around 0 degrees centigrade. Now, if you increase the temperature to the ice, what is happening? So this is my container. In this container, I have some ice cubes. Okay. So what I'll do, I'll start doing heating process. I'm heating this ice. So in the first stage, what is happening? You have ice. Okay, so that is the boundary of solid phase. Now, if you still increase the temperature, what is happening? Slowly, this ice is being converting into water. That means some portion is with water and some portion with ice cubes. Okay, so you have here the liquid phase. So this is completely liquid phase. That means after 0 degrees centigrade, the ice is being converting into 0. Okay, so that is the concept why the water is being freezed or being iced in the refrigerator. And once you bring out that ice to the room temperature, what is happening? Slowly that ice is being transformed into liquid state. So that is more than 0 degrees centigrade. That's why after this 0, slowly this solid is being converting into liquid state. So this is the liquid phase boundary. Now still if you heat that, what is happening? Complete ice cubes are being vanished and you have liquid, and this you can see here some vapors being formed. So that is the phase of vapor, that means steam. So that's why in the picture also you can see all the three figures clearly. So first picture is about the solid phase, which is in the form of ice. Second is in the liquid phase. Okay, so this is the liquid phase. And the third one you can see vapor. Steam is being coming out from the kettle. So this is an example of vapor phase. So total 3 different phases you have. So now you can see clearly. So first one is the ice cubes from minus 30 to 0 degrees centigrade. That this will be in the form of solid. So if you start raising the temperature from 0, slowly what is happening? That solid is being transformed into a liquid state. So this is the liquid. Then still if you further increase the temperature, so what is happening? Your water is being converting into steam. So this is how you will get all the 3 different phases. Now if you observe this figure clearly or the graph clearly, what is happening here? There is some point where all the phases are being contacted to each other. So this point is called as triple point. Triple point is nothing but where all the 3 different phases are being contacted with each other. That means there is a presence of solid, liquid and vapor. So all these combinations, when they are meeting at one point, that point is called as a triple point. So this point, if you observe, when you observe physically in a kettle, if you keep that ice and if you burn, what is happening? So this is the solid particles that is in the form of ice, and at some point you will get liquid and you will get some vapors. Okay, combination of all the three will gives the triple point. So that is shown exactly at this point. So this point is called as a triple point where all the 3 boundaries, solid, liquid and vapor boundaries are being contacted with each other. That point is called as a triple point. So this is the diagram how all the 3 are being formed. So here you have liquid, solid and vapor. So this point is called as a triple point. And each red color indicates for the boundary. So this is the boundary for solid and this is the boundary for liquid, and this is below this all the things are in the form of vapor. Above this vapor you can get liquid, and left to that liquid you'll get ice. So this is how you have to draw the phase diagram for a given H2O or the water. So each region shows an example of its phase. Each region is showing its phase, whether it is a liquid phase, solid phase, or vapor phase. Now, what is the importance of these phases? As I told, as we discussed in the previous slides, this phase transformations gives the characteristics of the given material. Now, suppose in the solid form, this is in the form of ice cube. Now, if you compare the characteristics of the ice with the water, so there are a lot of changes with the characteristics, even the properties changing. Similarly, if you compare the solid with the vapor, so there are a lot of difference with the characteristics as well as the properties. And we are trying to know what is the melting temperature also for the water. So what is the melting temperature? Beyond 10 degrees centigrade, the ice is being melting. So before that, it is not being melting. So if you want to melt the ice, you have to burn or you have to give the heat above 0 degrees centigrade. And if you want to convert that water into steam, then you have to increase the temperature above 80 degrees centigrade. Like that, we are trying to get those information with the help of these phase diagrams only. Similarly, for any type of metal, you have to draw these phase diagrams. Once you get these phase diagrams, it is very easy for us to identify the melting temperature, casting temperature, the mechanical properties, the microstructure also. Even the microstructure, if you see, before melting the ice, it's have its own microstructure. Once if you melt that ice and if you again observe the microstructure of water, it is in the form of different. Similarly, the vapor. So like that, even the metals, whatever the copper or nickel or iron, what are the things you are taking, these will have its own characteristics depending upon the temperature. If the temperature is increasing, it is being transformed into other phases. So depending upon those phases, you are getting these informations of casting, melting point temperatures, the crystallization temperatures, the physical properties, the microscopic structure. So all these informations we are getting with the help of these phase diagrams. That's why one need to understand how to draw the phase diagrams and what is the importance of these phase diagrams to incorporate in the applications. Now, if you go further, you have some basic definitions. What is the component? Generally, component is defined as a pure metals which is composed of some alloys. What is a component means? The component is a pure metal which is composed of some alloys. That is called as a component. And next, system. System refers to a specific body. Why we are discussing all these things means, next coming topics, we are mostly using these frames like a component or a system. So once I'll tell it as a component, then you have to understand that a component is a pure metal which is composed of some alloys. Component refers to a pure metal which is composed of alloys. And a system refers to a specific body. Some specific body refers to a system. Like that, these are some of the definitions where we can using these terms to describe some of the concepts. Okay, next. Now, what is solubility limit? Solubility limit is very, very important. So, if you want to dissolve any metal into the liquid, you have to know at what temperature the metal is being melted into the liquid. So, that gives information about the solubility limit. Now, if you take an example of water and a sugar. So, in a glass of water, slowly if you are pouring some sugar granules, what is happening? Slowly it is getting dissolved. Now, if you still further increase the quantity of sugar, it will dissolve. Further, if you increase the quantity of sugar, what is happening? Already there is some sugar syrup inside. So, there is no space for that additional sugar to dissolve into the liquid. So, what is happening? You can't further dissolve any more sugar into that glass of water where already some sugar solution or sugar syrup is there. So that is the maximum limit. At what point you can still adding, but there is no dissolution of the sugar into the water is called as a solubility. So that is the maximum limit where the sugar can dissolve or any metal can be dissolved into the water or the liquid. Initially, slowly at the starting point, the sugar is being dissolved. Still, if you are adding some more sugar, that is being dissolved. But what is happening there? The density of that liquid is increasing. If the density of the liquid is increasing, what is happening? If you add still more sugar, you can't try to dissolve that. Why? Because you are forming already a sugar syrup inside. So that is a main example to define a solubility limit. That means further this solubility limit, you cannot add. Though if you are adding, what you are getting? You are not getting anything. You are just getting that whatever the sugar granules are there, they are settling down inside. So at that point, what you're getting some liquid as well as some sugar granules inside. So beyond the solubility limit, you cannot add any metal. So that's why if you want to mix any metal into the solid, into the liquid, so there is some limit. So that limit is called solubility limit. Before solubility limit, you can easily dissolve that metal into the liquid. Beyond the solubility limit, you cannot add or you cannot dissolve any type of metal or alloys into the liquid. So that is the definition of solubility limit. So many alloy system at some specific temperature, that is very, very important. At some specific temperature, again, if you increase the temperature, the solubility limit also increases. So these are two proportional to each other. If the liquid, if you keep at normal temperature and if you keep it another liquid with a 100 degrees centigrade liquid, so what is happening? The solubility limit difference between these two will have a higher in the temperature liquid. That's why with increase in the temperature, there is a rise in the solubility limit. So these two are proportional to each other. So that's why the temperature plays a key role in this solubility limit. So the maximum temperature, the maximum solubility limit you'll get. But the addition, the definition exactly is beyond that solubility limit, there is no chance of solubility formation. So to illustrate this example, mainly we are taking the water and sugar as an example to explain this solubility limit. And how to draw the solubility limit graph also we'll see in the further slides. So initially sugar is added to water. So at that state, what you are getting? You are getting a sugar syrup formation, is it not? Initially you are taking some glass of water. In this you are adding, so you have some water here. So you are adding some sugar here. So what is happening? It is being mixed and you are getting some water solution or some sugar syrup. So after that, if you still add some sugar, so there is an increase in the quantity of sugar, but still, so there is some liquid. Since there is some liquid inside, so we are getting some solution. But still, if you add, there is no scope of water. The water content is getting reduced, but the sugar, whatever the thing you are adding, is being increasing. So at this point, there is no chance of dissolving. So that maximum point where the water can be dissolved into the sugar is called as a solubility limit. That means if the solubility limit is reaching, though you are adding any metal or sugar in this example, it cannot be dissolved. It will settle down at the bottom of the vessel. So at this time, the solution is not capable of dissolving any more solution. Okay, at this point, there is no chance of dissolving any more sugar, though you are adding. What is happening? Just it is getting settled down at the bottom of the container. Okay, so at the bottom of the container, whatever the extra sugar is there, which is crossing the solubility limit, it is being settling down inside at the bottom of the container. So in this case, what are the two things you are identifying here? So if this is the example, after the solubility limit, you can observe some sugar particles, undissolved sugar, and you can identify some sugar water syrup. So this is sugar crystals and this is sugar syrup. So here having two separate substances inside this. So first one is what? Sugar syrup, and second one is what? Whatever the undissolved sugar is there, sugar crystals. So two components you're having in this case. Okay. So the solubility limit of sugar in water depends upon the temperature again. So temperature plays a very main role here. So now slowly, if you increase the temperature, again the solubility limit will rise up, so that you can add still more sugar if you increase the temperature. This is the maximum temperature, then these are the two components you are having. So with these two components, how to draw the phase diagram, we'll see. Now, if you see this graph, about the x-axis you have sugar and water, and sugar is starting with 0. That means the quantity, how much sugar you are adding. Initially it's 0, and water is 100%. That means in a full glass of container, you have 100% of water and 0% of sugar at initial state. And that is the around the x-axis. And if you see along the y-axis, you have the temperature, which is in degrees centigrade. So in the x-axis, 0 of sugar, 100% of water. Now, x-axis refers to composition weight percentage. How much amount of sugar or how much amount of water you are giving refers to the x-axis. That's why it is called composition weight percentage. How much composition of sugar and water are there refers to this composition percentage. And this y-axis refers to your temperature in degrees centigrade. Of course, at this side you have in 400 degrees centigrade. So this you can neglect. Now, if you observe, at initial state, what is having 0% of sugar and 100% of water. So wherever you can see, since you have only two materials here, one is sugar and another is water. That's why wherever you see, the sum of the two weight percentages should be equal to 100. That's why if you add these two, you're getting 100. 20 plus 80, you're getting 100%. 40 plus 60, 100. 60 plus 40, 100. 80 plus 20, 100. And 100 plus 0, 100. So total, it should be 100%. Now, if you observe clearly, in the x-axis, sugar is starting from 0, increasing by 20%, still increasing by 40, still increasing by 60, 80 and 100. Okay. Now, if you see the water percentages, initially it is 100, later it is becoming 80. Why it is becoming 80? Since you are adding 20% of sugar, 20 weight percentage of sugar, that's why the water is being reduced to 80. After that, still if you are increasing that sugar content to 40, so the water is getting reduced to 60. But total should be 100. That's why you're getting 60 here. Still, if you add sugar of 60 weight percentage, water is getting reduced to 40. So this is the maximum limit where if you still add some additional sugar into the water, it cannot be dissolved. That's why if you see in the graph, this red line indicates the solubility limit. So this is the maximum limit. This is the maximum limit where the metal or some alloys can be mixed in the water. Beyond that limit, there is no chance of solubility of any type of metal or alloys. So that's why if you see before this red line, that is red curve, that is solubility limit, you are having a liquid solution, that is liquid syrup solution you have before the solubility limit. Now slowly after crossing, what is happening here? As we discussed, it is having two substances. One is what? You have already some sugar syrup, and another is what? What are the additional sugar you are adding? It is being settled down inside the container. That's why you're getting two substances here. First one is liquid solution and the other is solid sugar. So two substances you are getting. That's why beyond this solubility limit, you are getting these two. So these two you have to show in the phase diagram. So if you see this clearly, you can understand. So 60 weight percentage of sugar, when it is mixed with 40% of water, so that is the maximum limit you are getting. So that's why This is the line where you are getting this solubility limit, and this solubility limit is being increasing with the temperature. If you see temperature, if you increase the temperature, this solubility limit is also increasing. But this is the maximum solubility limit. Now, since you are increasing the temperature, this solubility limit line is also being increased. And before the solubility limit, you are having only the liquid syrup solution, that you have to know, because whatever the metal is there, it is being dissolved completely inside the water. That's why you are getting the liquid solution or liquid syrup. Now, beyond this, if you cross this 60% of sugar with 40% of water, what is happening? You can't dissolve anymore. But you can have two substances. What are those two substances? In that container, you have the liquid syrup already existing. But what are the additional sugar you are adding? They are being settled down inside the container. That's why you are writing two things here: liquid solution and plus solid sugar. So beyond and before, you have to show the liquid syrup, and beyond that, you have to show liquid syrup plus the additional solid sugar. So this is how you have to represent the H2O solubility of sugar with water phase diagram. Now, the solubility limit, what are the solubility limit is there, is represented as a nearly vertical line. So this solubility limit is represented by a vertical line in this figure. So this is how you have to show. How to show? Don't make it some curve type like this. It should be a vertical line. Why vertical line means, since it is raising with the temperature, since it is being raising with the temperature, so this also should be raised as a vertical line with the temperature. So this is how you have to represent. And the composition and temperatures to the left of solubility line, only the liquid syrup exists. Now, why are you drawing all these things? So one need to know what is the melting point, what is the solubility limit of any type of metal. So that's why if you know this phase diagrams, it is very, very easy for us to identify the solubility limit and where is the liquid content is there, and where is the solid substance is there, and where is the combination of these solid and liquid is there. You can easily identify with the help of this phase diagrams. That's why what we are showing here, we are trying to show the solubility limit as a vertical straight line, since it is being increasing with the temperature, and also the composition and temperature. What is the composition here? The composition percentage of sugar with water. The composition sugar percentage of sugar with water. These are the compositions. So if you mix 60% of sugar with 40% of water, then there is the maximum solubility limit. So that we are understanding with the phase diagrams. If it is beyond, that means if you add 80% of sugar with 20% of water, there is no chance of dissolving. So like that, this composition percentage and the temperature help us to identify at what point you are getting the solubility limit of any type of material. So this here, to explain this, we are taking a small example of sugar and water. It is easy for us to describe and easy for us to understand. Similarly, if in any solution, if a nickel or copper is being added, so at what point you are getting that liquid, at what point you are getting the combination of liquid and solid, and what point you are getting into solid. So all this information can be obtained with the help of these phase diagrams. So that's why when you are representing this phase diagram of this, you have to show the liquid syrup towards the left side of the solubility limit curve, and towards the right side of the solubility curve, you have to show both the liquid solution as well as the solid sugar. And also intersection. Where is intersection here? Intersection of the given temperature to the coordinate. So here it is being intersected. So this point is called the maximum solubility limit. So this is how you can identify at what point is the solubility limit for sugar with respect to water weight percentage. And if you want to know at some temperature, some X temperature, what is the value of the solubility limit? So how to identify? So here you have an example. For example, at 20 degrees centigrade, the maximum solubility limit of sugar in water is 65%. So you have to draw at 20 degrees centigrade. So you have to draw this exactly parallel to your x-axis from 20 degrees. Draw a straight line, and then you drop a line towards the x-axis. So at this point, you are getting 65 weight percentage, and this is the 20 degrees. Similarly, at what point you want to have, it is very easy for us to drop, or you have to stretch the lines along x and y axis. If you stretch along the lines along x and y axis, then it is very easy for us to identify what is the maximum percentage of sugar with water at particular temperature. So in this example, we have taken at 20 degrees centigrade, what is the maximum solubility limit of water means. So what you're trying to do, you're just stretching the line towards the y-axis and just dropping on the x-axis, so that at this point you have to see. Similarly, suppose I want at 60 degrees centigrade, what I have to do? I have to draw a line from y-axis and drop a line at x-axis. So what is the value you are getting here? You are getting 70 weight percentage. So like that, you have to stretch the lines along x-axis and y-axis to get the information of what is the weight percentage with respect to sugar and water at particular temperature. That's why, see, if you observe here, initially at 20 degrees centigrade, what is the value you are getting here? 65 weight percentage at this point. Now if you see at 60, what is the weight percentage you are getting? 70. Similarly, if you go with the 80, draw a line, you are getting at 80 degrees centigrade, you are getting 80 weight percent. That means it is increasing with respect to temperature. So how much temperature you are increasing, the weight percentage, that is the solubility limit, is increasing. So this is how you can justify the correlation between the temperature as well as the solubility limit. So these are directly proportional to each other. With rising the temperature, the solubility limit is also being increasing. So this is how you have to identify the percentages composition of any type of metal. Now, also, what is the main concept to understand the phase means? Also, the critical to understand the phase diagram is the concept of phase. So, what is that? Understanding of phase diagram is the concept of a phase. In order to understand the phase diagram, one need to know what is a phase. Okay, that phase is nothing but the solid, liquid, vapor transformations. So once you know this, it is very easy for us to understand the concept of phase diagrams. And also homogeneous portions. Homogeneous means same at a single temperature, at some temperature, the metal should be homogeneous at equal point. At any point, if you identify, it should be the same. That's why it is called as a homogeneous. And with respect to what? With respect to physical and chemical characteristics. So at 20 degrees centigrade, if the physical and chemical characteristics are same, then that type of system is called as a homogeneous system. If it is not uniform, then it is called non-homogeneous. So that is one of the concept. And every pure metal is considered to be a phase. Okay, every pure metal, that means a solid, one phase, liquid, another phase, gas, another phase. Like that, every pure metal can be described as a phase. And as best example is what? Sugar with water syrup. So this is the best example of identifying the three different phases of this example. And each has different physical properties. As we discussed in the water, so when it is in the solid form, when it is in the liquid form, and when it is in the vapor form, it has its own physical properties. Similarly, with that sugar water syrup, what is happening? Before it is being dissolved into the water, that's why it has some properties. After that, some sugar syrup is being formed with some dense material, and it is having another physical properties. After the solubility limit, what is happening? There is some sugar solution as well as sugar granules undissolved. So this is having another properties. So that's why with the help of this phase diagrams, it is very easy for us to identify what are the different types of physical properties which are being observed with respect to the temperature or with respect to the phase transformations. So if more than one phase is present, in a given system, each will have its own properties. Is it not? If the system is having one phase, it has its own properties. If the system is having two different phases, so system I told some specific shape. Okay, this system now it is in the form of a sugar solution. It is having single phase, then it has its own properties. Now the same, after crossing the solubility limit, it is having two phases. One is liquid, another is solid, which is being settled down at the bottom. So it has its own properties. That's why each phase will have its own physical or chemical properties. Now, when two phases are there, it is not necessary. In some cases, it is not necessary, which can have different physical or chemical properties. It depends upon the type of metal what we are taking. And when water and ice are present in a container, two different phases are available. So that we have seen in the previous example, one is in the solid form, another is in the liquid form. So these two forms or two phases will have its own properties, identical. And what is a homogeneous? What is homogeneous? We are discussing about a single phase system. When a single phase system is there, it is termed as homogeneous. Why single phase? Single phase systems will have its own physical and chemical properties. It will not affect with any other thing. So that's why it is homogeneous. If any type of system is having more than two phases, then that type of system is called heterogeneous system. Okay, homogeneous means a single phase. If it is having more than two phases, then that type of system is called heterogeneous systems. And what are the examples of these heterogeneous are like metallic alloys, which is composing of ceramics, polymers, and composite systems. So these are having different additional materials. So because of these composites and polymers and ceramics, it is having multiple phases. That's why these are called as a heterogeneous type of system. If any single system is there, single phase is there, then that type of system is called homogeneous. So since you are having some additional metals or additional alloys into the metal, then that type of thing is having more than multiple phases, more than one phase. That's why it is called heterogeneous system. So mainly the phase interact in such a way that the property combination with multiple phase systems. So depending upon the phase systems only, the characteristics of the metal will alter. So mainly it depends upon the phases. How many phases are there? Depending upon those phases, these properties are being varying to each other. And microstructure. So main thing is what? The phase diagrams are giving us the microstructure of the given metal. And these microstructures can be identified with the help of using the optical or electron microscopes. So these microstructures again varies with the temperature, varies with the phases, okay, varies with the pressures. So all this can be identified with the help of the phase diagrams. And in metal alloys, microstructures are characterized by the number of phases present. So how many number of phases are present inside the metallic structure or microstructure, and these can be characterized, whether it is having one phase or two phase or three phase. By seeing the microstructure, it is very easy for us to characterize the metal alloys. And the proportions can be arranged or distributed with the help of the heat treatment process. So how much amount of heat has to given to the metal in order to get the uniformity or to increase the properties or to improve the properties can be done by the heat treatment process. And also when you do the cooling process, again the microstructure varies, again the properties varies. So all these things depends upon the phase diagrams. And what is equilibrium system? Equilibrium is another essential concept to describe the terms in thermodynamic. That means uniform distribution, equilibrium. It has to balance to each other. How much amount of heat you are giving to the system, it has to be balanced. So this type of system is called as a free energy. So what is free energy? So free energy is a function of internal energy of system, which can be randomness or disorder of the atoms or molecules. And a system is equilibrium if it is having less free energy. If any system is having minimum free energy, then that type of system is called as a equilibrium system. So thermodynamically, the quantity should be maintained equilibrium, then that type of system is called free energy. And if a system is set to be an equilibrium, then you should have a minimum value of free energy. So these are some of the terms you need to understand while preparing any type of metal alloy. And so if you want to have any references regarding these phase diagrams and how to find out the composition percentages of the different components, you can be get from these references. That is Introduction to Physical Metallurgy by Tata McGraw-Hill, and another is Essential of Material Science and Engineering by Thompson, and another book you can refer as Material Science and Metallurgy, which is Everest Publications, and the last book is Material Science Engineering by Ville. So these are some of the references where you can identify the phase diagrams and what are the different transformations of the phases and how these phases are important to identify the characteristics, the properties, the microstructure, and additional to this, what is the melting temperature, what is the crystallization temperature, what is the casting temperature. All these informations can be identified, can be acquired with the help of phase diagrams. So this is about the phase diagrams. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.